So today we're going to use modified unit analysis to solve a real-life problem, and this real-life problem has to do with the functioning of a laser. Now, it's my opinion that modified unit analysis is of little or no use unless we can use it to solve a real-life problem, okay? Up to this point, it is merely theoretical. It is used to reinterpret the equations of theoretical physics, but I think it is important to see how it can be applied. Okay, so application of MUA is the purpose of this video. So just as a quick review, in modified unit analysis, the units of frequency are cycles per second, and they're written like this. The cycle term, this little triangle corresponds to the cycle term, and so the units of frequency are cycles per second, and the units of wavelength are meters per cycle. And of course, the units of the wave period are seconds per cycle, and the units of the wave number are the inverse of the wavelength, which is the cycles per meter. So this is not that much different than standard unit analysis. The only thing I'm doing differently is I am implementing a symbol for the cycle term, and I am specifically introducing the cycle term into all of the equations that contain a cycle term. So in terms of the language, this constant would correspond to the energy of one photon. This would be the momentum of one photon, and this would be the mass equivalent of one photon. So this is the energy contribution, this is a momentum contribution, and this is a mass contribution. And these constants can be used both for light and for matter when matter is being modeled as a soliton, as in the John Mackin model. So what we're going to do next is we are going to convert the energy equation, so the standard Planck energy equation. We're going to convert the energy equation to a power equation, and the way we do that is we introduce a time parameter. We divide both sides of the equation by a time parameter, and we set t equal to 1. Okay, so we are dividing both sides by a time parameter, and that time parameter is equal to 1, as in 1 second. Okay, so now this equation is on a per second basis. Okay, and it also turns this into a power equation. So we also have to introduce a new unit. Okay, we have to divide both sides of the equation by a second term. Okay, so we have to divide this. So the HF needs to be divided by a second term, and the final output needs to be divided by a second term. And so what we end up with is we end up with this, the second terms cancel, and so we end up with joules per cycle, and the output of the equation has units joules per second, which are the units of power, the watt. Okay, so this is how we convert Planck's energy equation to a power equation, and as I said in the previous video, the reason I'm doing this is because the original black body experiments were done in terms of power. They were plotted in terms of wavelength per intensity, or sometimes they do frequency per intensity, and intensity has units watts per meter squared. Okay, and so the other thing we're going to do here is instead of in the power equation, because Planck's constant technically has new units, so joules per cycle, so instead of joules times second per cycle, the energy of one wave period, it is joule per cycle, the energy per cycle, which it basically is the same thing. So the energy of one wave period is the same as the energy per cycle. It's just a different way of writing it. And so what I do in this video is I use a different symbol. The delta P is the quantum of power, the cycle of power. It's numerically identical to Planck's constant. Okay, only I'm giving it a different symbol because it has different units. Okay, so now we have a power constant, which is the cycle of power. I refer to as the cycle of power, and this is the power per cycle, and this is Planck's constant, numerically equal to Planck's constant, but it is on a per cycle basis. And then I have a power equation where I use the delta P. I multiply this delta P by the frequency term. So this is E equals HF, but written in terms of power. And so the unit of this has units joules per cycle, so the constant has units of joules per cycle. Frequency has units of cycles per second. the cycle terms cancel, and you end up with joule per second, okay, the units of power. So the constant is, another way of looking at it is the constant is on a per cycle basis. So this is the power contribution of one cycle, okay, and the equation equal to HF is on a per second basis. Okay, so this conversion that I did here, where I converted the energy equation to the cycle equation, makes it perfectly clear. I didn't change anything. The numerology is still the same, but written in terms of power, it makes it abundantly clear that this equation is on a per second basis, and this is on per 1 second, okay? So this is the power delivered on a per second basis, sorry, the energy per second. So this is power. So power is always on a per second basis. It's not per 2 seconds or per 3 seconds or per 10 seconds. It is on a per 1 second basis. Okay, so this, converting this to a power equation, in my opinion, makes it abundantly clear that even the original E equals HF Planck's energy equation is on a per second basis. So this is the energy delivered in a 1 second time interval, which is what Juliana Mortensen has been saying all along. So the other equation that we're going to need to solve the laser equation is the force equation. And so the cycle of force is the cycle of power divided by the speed of light. Okay, that gives us a force constant. And so this is the numerical value of the force constant, and it has units of momentum per cycle. Okay, and then we write the force equation much like the power equation, where we say force is equal to the force constant times the frequency term. Okay, this is the same frequency term from this equation, only we are applying it to the force constant. So the units of this equation are, so the units of the cycle of force are momentum per cycle. The units of frequency are cycle per second. The cycle terms cancel, and you end up with kilogram meters per second, which of course are the units of force, so the Newton. Okay, so we've got two equations. We've got a power equation, we've got a power constant and a power equation, and a force constant and a force equation. And the force constant is on a per cycle basis. So this is the force contribution of one turn of the oscillation of the photon, of one photon, which is one oscillation. And the force equation is on a per second basis. Okay, so this is momentum per second. So this is momentum per cycle for the constant, and momentum per second for the force. Okay, so again, this is on a per second basis, and this is on a per cycle basis. Okay, so now we have all the tools we need to solve the laser problem. Okay, we've got the power equation, we've got a force equation, and now we're going to solve a real life problem. Okay, so here is a little document that I wrote up, and what I will do is I'll share this document in the description section when I'm done, and that way you can review it and make sure I didn't make any mistakes. Okay, so modified unit analysis, a practical example. Okay, so given an 0.516 watt laser emitting light with a wavelength of 726 nanometers, what force would the light emitted by such a laser exert on an external object? Okay, so the easy answer for this is force is equal to power times the speed of light, as we saw earlier. We take 0.516 and divide it by the speed of light, and we get the final answer right here. So this is the easy shut up and calculate version of or way to calculate this value. It's quite simple, but however, this doesn't tell us anything about what's going on under the hood. What is light power? What does that mean? What is the relationship between Planck's constant? What is the amplification factor of the laser? So to answer these questions, we're going to solve this problem using modified unit analysis and the associated cycle constants and equations that I just showed you. Okay, so in MUA, we are calibrated to the cycle, and therefore all the quantum constants are on a per cycle basis. Okay, so next we're going to talk about the constants that we need to solve the laser problem. So first we have the speed of light, which is exactly equal to this value here. The speed of light has units meters per second, and so clearly you can see that the speed of light is on a per second basis. Okay, this is the distance light travel in meters per 1 second. Okay, not per 2 seconds, not per 10 seconds, but per 1 second. So you can clearly see that these are the units so that the speed of light is on a per second basis. Okay, so light travels this distance per 1 second. Okay, so then next we have the power constant, which is the this value here, Planck's constant, but it has units joule per cycle, so it is on a per cycle basis. Okay, this is the power contribution of one photon, of one cycle, one wavelength, one period of a wave. Okay, and this could be a traveling wave, or it could be a standing wave, as in John Macken's soliton model. Okay, so then we have a power equation, which is power is equal to the cycle of power times the frequency term. The cycle of power has units joule per cycle. Frequency has terms cycle per second. The delta terms cancel, and we end up with the units of joules per second, or the watt. Okay, so clearly joule per second is on a per, so similar to the speed of light. Okay, similar to the speed of light, this power equation is on a per 1 second basis, not per 10 seconds, not per 100 seconds, but per 1 second. Okay, and so the power constant, the cycle of power is on a per cycle basis, and the equation is on a per second basis. So then next we had the force equation, the force terms, and so we've got the force constant, which is the cycle of power divided by the speed of light. And this gives us this value here, which has units of momentum per cycle. Okay, then we have the force equation, which is the cycle of force times the frequency term, and this is the same frequency term as the power equation. And so the cycle of force has units momentum per cycle, and frequency has terms cycle per second. And so the cycle terms cancel, and you end up with kilogram meters per second, which of course are the units of force, or the Newton. Okay, so these are all the tools we're going to use to solve the laser problem. But I also want to point out that the force term, the force equation here, is on a per second, okay, on a per second basis, per 1 second, not per 2 seconds, not per 10 seconds, but this is on a per 1 second basis. That's what per second means. And so the force constant is on a per cycle basis, and the force equation is on a per second basis. So now we have all the tools we need to solve this problem in the domain of the modified unit analysis. Okay, so in the Ohm particle model using modified unit analysis, the power constant delta P is interpreted as the power contribution of one cycle, of one photon, of the oscillating system. Okay, so this can be a traveling wave, this can be a standing wave, as in the soliton model, and so this is the power contribution of one photon. So similarly, the force constant is interpreted as the force contribution of one cycle, or one photon. So that corresponds to one cycle, one period, one wavelength, one oscillation, one photon. Okay. So step 1 is to calculate the wave period and the frequency of light of the light wave using the wavelength of 726 nanometers. Okay, so in what I'm doing here is I'm going to be using the frequency term, but I'm also calculating the time period just for the sake of argument. Okay, so to calculate the time period, you take the wavelength and divide it by the speed of light, and to calculate the frequency, you take the speed of light and divide it by the wavelength. So these are inverses of each other, these are reciprocals of each other. And so a 726 nanometer wavelength is actually converts to 7.26 times 10 to the minus 7 meters, okay, because we are in the MKS system, so we need to use meters. So this value divided by the speed of light is 2.42, etc., times 10 to the minus 15 seconds per cycle, okay? So you've got meters, the units of wavelength are meters per cycle in modified unit analysis. The units of the speed of light are meters per second. Okay, so because these are in the numerator, the denominator, you have to reverse them when you multiply. So meters per second dividing by meters per second is the same as multiplying by second per meter. So the meters cancel, and you end up with seconds per cycle. Okay, so that's how modified unit analysis works. The frequency term, of course, is the reciprocal of that. So you end up with 4.12, etc., times 10 to the 14th cycles per second, and that's in terms of hertz. Okay, so step 2, what we need to do is calculate the power contribution of the unamplified light source. Okay, so this is pre-lasing, pre-amplification. This is the power contribution of the unamplified light, which I am referring to here as P sub U, or PU, if you may. So P sub U is equal to the cycle of power times the frequency, which we had, which the frequency, which is here, and you end up with 2.736, etc., times 10 to the minus 19 joule per second. Okay, so the cycle of power has units joule per cycle, frequency has units cycle per second, and so we end up with the units of joule per second, or the watt. So using this value, we can now do step 3, calculate the amplification factor of the laser. Okay, so we take the power of the laser, 0.516 watts from the original question, and we divide that by P sub U, which is the power contribution of the unamplified light. Okay, and when you do that, you get this value here, 1.885, etc., times 10 to the 18th watts per watt. Okay, so this is unitless, of course. It is an amplification factor, so it's unitless. And so this is the amplification factor of the laser light, right, given the frequency of light that was given in the original, or the wavelength of light that was given in the original question. So in short, we took the power associated with one cycle and multiplied it by the frequency to get the power associated with 1 second. And this, of course, is the power delivered by a single electron jumping up and down a level. Okay, so you can think of the electron jumping up and down a level creates one unit, creates one cycle, okay, one cycle of the wave. And so each time it jumps up and down, it creates one cycle of the wave. That's at least how I see it. And then you multiply that by the frequency to get the number of ups and downs in 1 second. Okay, the energy associated with all the ups and downs in a 1 second time interval. So in modified unit analysis, this wave amplitude interprets as the number of waves that are superposed on each other in because everyone knows that light can have superposition. You can have waves on top of each other. Okay, so everyone knows that when you take two waves and have them, make them coherent, make them have the same phase, then they will superpose and you'll get a higher amplitude, you'll get a higher intensity of the light. Okay, so here you see every time the waves are coherent, the amplitude is bigger, and every time it's the smallest when they are the furthest apart. Okay. So when they are far apart, the amplification is very small. Okay, so everyone knows that. I just wanted to mention it because I think it's important to talk about what this amplification factor means. It is literally the number of waves that are superposed on each other, and you can see that this is a very big number. So for this particular laser, we have 1.885, etc., times 10 to the 18th waves superimposed on each other. So you can imagine that this intensity is going to be quite high, and this is why, of course, lasers are very powerful. Okay, so that is what this means in modified unit analysis. That is what the amplification factor means. It's logical, it makes sense. But in the standard language, and please correct me if I'm wrong, but it's my understanding through conversations with other people that this value here corresponds to the number of photons. Okay, the number of photons. And so without a really good visualization of what a photon is, I find that saying that this is the number of photons that the laser is emitting at any one time it's a strange language. It's not too far from the truth, but I would rather say that this is the number of waves that are superimposed through the lasing process, through the making the waves coherent. This is the number of waves superimposed, but you could also think of it as this is the number of waves that are hitting a detector. So you can imagine this wave is moving from left to right coherently, and that there are 10 to the 18 waves superimposed on each other at any one time. Let me see if I can get this a little closer together. Okay, so we can imagine that there are 10 to the 18 of these waves superimposed, and so when this crashes into the detector over here, the detector is going to read a higher intensity signal. So, more waves are going to be crashing into the shore of the detector at any one time. And so this is basically, you can think of it as the number of wave fronts that hit a detector, some certain area of the detector at any one time. So that is where the let me just go back to my PowerPoint here. That is where the watts per meter squared, which are the units of intensity. Okay, so which is what we were reporting in the black body, the original black body experiments. So this is how I explain modified unit analysis. So I'm saying it differently, I'm interpreting it differently. This number is not the number of photons. Okay, it is the number of photons that hit the detector at any one time, wave fronts. Okay, so a photon generates a wave front, and there are 10 to the 18 wave fronts hitting the detector at any one time. Okay, so that's how modified unit analysis interprets the wave amplitude that we just calculated. Okay, but we're still not done with the problem. Okay, we still have to calculate the power and compare that to the original calculation of the power to make sure that we're doing things correctly. Okay, so now we have the amplification factor. Now we want to calculate the force. Okay, the original question is, what force would the laser light exert on an external object? Okay, so I'm going to, first of all, we have we're going to be using the quantum of force, okay, the quantum of force, which we talked about up here, which is the power divided by the speed of light. Okay, so step 4, we're going to calculate the force contribution of the unamplified light source. Okay, so the force associated with one photon, so this is the constant, the force constant is the force contribution of one photon. Then we have the frequency term like before, and then right there, the power one. So we're using the same frequency, only now instead of calculating the power, we're calculating the force contribution of 1 second worth. Okay, so this is the force contribution of one photon, one cycle, one wavelength of light being emitted from the electron jumping up and down. So electron jumps out, up and down, generates waves where each cycle contains or delivers this force. Is capable of delivering this basically momentum per cycle. It's a momentum per cycle. It's force-like, but it's not force because force is on a per second basis. Okay, so anyway, so we've got the quantum of force multiplied by the frequency is equal to 9.1268, etc., times 10 to the minus 28 momentum per second. Kilogram meters per second. Okay, this is the force. This has units newtons. So the delta force has units of momentum. So here P stands for momentum, and I don't like using P here. I want to find another symbol for momentum because in mainstream language they use P for momentum, and that's the only reason I did this here. But this is really kilogram meters per second. Let's go here. So it's really kilogram meter per second per cycle and kilogram meters per second. Okay, so I just shortened it here for the sake of looking better, which is not always a good thing. Okay, so I don't like that I did this, but so we've got momentum per cycle, cycle per second. You get momentum per second, kilogram meters per second with the units of the Newton. Okay, so we are calculating the force. So like the power term, so the cycle term is the force contribution of one cycle. When you multiply that by frequency, you get the force contribution of 1 second of the number of the frequency, so the number of oscillations in 1 second. So this gives us the force delivered by one atom jumping up and down this frequency times in 1 second, and they're generating waves. Electrons don't emit waves, they generate waves through their motion in space. We know this is true. So the electron is jumping up and down in the atom, generating waves, and This is the force delivered by 1 cycle. This is the force delivered by 1 second in a 1 second time interval. Okay, so that's force has units on a per second basis, not per 2 seconds, not per 10 seconds. It's on a per 1 second basis. Okay, so we've got the power equation and the force equation in terms of per second. And we have the amplification factor. So now, step 5, we can, using the amplification factor, we calculate the force that the laser will exert on an external object. Okay, so now we are going to multiply the force of one wave. Okay, so the force of generated by one is like the red wave. Okay, the force of one wave as the wave hits the detector. Okay, and then we're going to multiply that by the amplification factor. So we're going to take F sub u, or FU if you may. We're going to take FU and multiply it by the amplification factor, and we're going to get 1.71190 times 10 to the minus 9, which is exactly the same value that we calculated to all the digits of precision. So it ends with 2464. And this ends with 2464. It's exactly the same number to all the decimal places used for both calculations. Okay, so here we're able to calculate force the hard way, but the way I did it here, we get a clear picture of what is going on. At least this is how modified unit analysis interprets laser light. It interprets laser light as, so 1 cycle, okay, can deliver a certain amount of energy to the detector at any one time. Okay, per cycle, on a per cycle basis. And on a per second basis, you're going to have more units of more photons hitting the detector at any one time. Okay, so we go from photon to what historically has been called the photon, but it's not a photon, it is the energy delivered on a per second basis. And therefore, this cannot be the energy of a fundamental particle called the photon, because different frequencies generate different outputs of this equation. And so that is where I ran into trouble in the first place, because they refer to the photon as a fundamental particle, but the energy output of this equation changes depending on the frequency and or the wavelength of the light source. And so this cannot be the energy of a photon, and when you model the equation as a power equation, you can clearly see that the output of this equation is on a per second basis. So this cannot be the energy of a fundamental particle, but this can be the energy of a fundamental wavelength. Okay, wavelengths are fundamental. Okay, they're fundamental because each wavelength is different size, but they are fundamental in that they are just 1 cycle. Each wavelength has something in common. They each have a cycle, they each have a wave period, they each have a wavelength. Okay, so that makes this more fundamental in terms of an entity than the historical photon. Okay, that's my opinion, but I think this kind of shows, this is sort of a mathematical proof that the photon doesn't exist as a fundamental particle, but the wave front does. Okay, a wave front, when it crashes into the shore of a detector, does appear particle-like. Okay, when a wave front crashes the shore on my beach and I'm standing when it's crashing, it hurts a little bit. There's particles hitting me. Of course, the particles are the particles of the water. Okay, when the waves hit the shore of the detector, it is my opinion that it is delivering waves of ether, of whatever the medium for the propagation of light is. Okay, so it is the wave, this is a wave of ether. If it's a light wave, it's an ether wave that is propagating through the ether, and what crashes into the shore of the detector, the atoms, are these waves. And of course, then the electrons absorb the wave and they jump up a level, and then they, when they jump down a level, they wiggle the ether, and the ether, another wave gets generated. And so this is how waves are formed in the Ohm particle model using modified unit analysis. So MUA gives us the tools that we can use to solve a problem, a practical problem involving power and force, which of course is what the electrical engineers would like. Electrical engineers like to calculate power and force, and physicists like to calculate energy and a momentum. Okay, I find it more practical. That's why I call it a real life practical example. Because in practice, nobody cares about momentum and nobody cares about energy. Not really. We care about force and we care about power. Okay, we want to know how much power we're delivering to our house to run our electronics, and we want to know what force, when I apply a force to something, when I set something into motion, I want to know what force that's going to have. I care about power and force. And for some reason, physicists are focused on momentum and energy. And of course, you can't measure momentum, right? You can only measure force. So you can't really measure momentum directly. You can only measure force, okay? And you can't measure energy directly. You can only measure power, right? You can't measure energy. You can only measure changes in energy, and changes in energy are temporal, and so they're technically power rather than energy. So you can't measure energy, you can measure power. You can't measure momentum, but you can measure force. And so it seems like physics, the language of physics is focused on things you can't measure, which is why you have the uncertainty principle, and engineers and electrical engineers focus on things that you can measure, which is power and force. Okay, without power and force, you can't do any kind of engineering. Okay, so this is why I like modified unit analysis, and I like writing the equations in terms of power and force instead of energy and momentum, because these are things that are useful in real life. So that's why I call this a real life problem. It's a real life example. Okay, and so this is why I like modified unit analysis. Okay, this is why I'm promoting it. This is why I'm working on it. I'm more just concerned about the language. The problem is with the language, like I always say. And so I'm trying to fix the language so that we can solve problems in a way that is logical and makes sense. This is completely logical. What I did here is so easy. It's so logical. Okay, you calculate the quantum of power. You multiply by frequency to get the power, the unamplified power. You use that to calculate the amplification factor. So now you know what the amplification factor is. And then you do the same thing with the force. So now you can calculate the force, multiply it by the amplification factor to get your final value. This is the long way. This is the long way to solve this problem, but it is also a logical way to solve this problem. Okay, so I'm going to leave it at that, and I'll be back. And I hope you had a great, if you're in the States, I hope you had a great Thanksgiving weekend. We had ours, of course, back in October. And so I hope that everything is good. And, well, again, I'll be back.